Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the effect of harmonics on the induction motor performance. We have just started to analyze what are the various harmonics present in a typical non-sinusoidal waveform. So, we will continue from that point. Now, here we have 3 square waves. Let us say we have 3 square waves here. So, this is for phase A, and this square wave can be coming from a 3 phase inverter. So, we have for phase A, and similarly we have for phase B, this is the output of phase B, which is also a square wave, and this is shifted from phase A by 2 pi by 3, lagging behind phase A by 2 pi by 3, the output is square wave. And similarly, VCN, these are the 3 voltages VAN, VBN and VCN, and VCN is also a square wave which is shifted from VBN by 2 pi by 3 or 120 degree. So, this is also a square wave. So, this is supplied from a square wave inverter. Now, when we apply this 3 phase voltages to an induction motor, what happens? The induction motor has got 3 phase windings. So, the 3 phase windings will resemble like this. So, we have phase A, phase B and phase C. So, this is the stator. So, we have let us say phase A here and phase B and phase C. Let us say we have the neutral here and we are applying between one phase and the neutral. So, these are the 3 phase voltages, and the rotor is, let us say, short circuited rotor, which could be a cage rotor or a squirrel cage rotor. So, when we apply this 3 phase to the stator of the induction motor, what happens? This is the rotor. So, this square waveform consists of many harmonics, and we can very easily say that this square waveform has got only odd harmonics. So, we have a fundamental component. So, if we analyze by Fourier method, so we can use Fourier analysis can be used to various frequency components. Now, if we take the first harmonic, that is a fundamental one. So, we can call this to be VAN1, that is equal to some magnitude V1 into sin omega t. What about phase B? Phase B for the fundamental, the first harmonic, that is V1 sin omega t minus 2 pi by 3, because phase B is shifted from phase A by 2 pi by 3. Similarly, phase C, VCN1 is equal to V1 sin omega t minus 4 pi by 3, or that is equal to V1 sin omega t plus 2 pi by 3. Now, this is about the fundamental component. Using the Fourier analysis, we can find out the various harmonics, and in this case there are only odd harmonics because of quarter wave symmetry. odd harmonic is the third harmonic. So, the third harmonic would be V A n 3, that is the third harmonic amplitude sine of 3 omega t, because this is third harmonic. Phase B, B n 3 is V 3 sine 3 of omega t minus 2 pi by 3, because this is shifted from phase A by 2 pi by 3, and that is equal to V 3 sine of 3 omega t. And for phase C, third harmonic is V 3 sine 3 omega t plus 2 pi by 3. So, if we take it into the bracket, so this is V 3 sine 3 omega t plus 2 pi, and sine function is repetitive with the 2 pi. So, we just have sine 3 omega t. So, what we find here, that the fundamental component represents a positive sequence component. We can call this to be a positive sequence component, where the phase sequence is ABC. So, A followed by B followed by C, and then it repeats A, B, C, and then A, B, and C. What about the third harmonic? Now, if we see the third harmonic, we see that the third harmonic are cophasal, because here we have 3 omega t, here also we have 3 omega t, and same 3 omega t here. So, they are actually cophasal. So, we can say that they are cophasal. There is no or we can choose to say this is a zero sequence. This is zero sequence component. It means phase A, phase B, phase C are in the same phase. Now, let us try to see the fifth harmonic. We have all the odd harmonics present here. The fifth harmonic will have this nature V A n 5. We can use the Fourier transform to find out the fifth harmonic amplitude V 5 into sine of 5 omega t. For phase B, amplitude of the fifth harmonic into sine of 5 of omega t minus 2 pi by 3, and that is equal to V 5 sine 5 omega t into 10 pi by 3 minus 10 pi by 3, which is same as V 5 sine of 5 omega t. If we simplify this, we will see that this is same as plus 2 pi by 3. And what about the phase C for the fifth harmonic? C n 5, that is V 5 sine of 5 omega t plus 2 pi by 3, because phase C has to be shifted accordingly with respect to omega t. This is omega t plus 2 pi by 3 or 120 degree. Pi is 180, 2 pi by 3 is 120 degree. So, here it is 5 of omega t plus 120, and that is equal to, if we simplify this, this is V 5 sine 5 omega t minus 2 pi by 3. Now, we see here that the fifth harmonic represents a negative sequence component, because phase B is leading phase A by 2 pi by 3 and phase C is lagging phase A by 2 pi by 3. So, this represents a negative sequence component. So, it means the phase sequence here is A After that, lagging phase A is not phase B, lagging phase A is C, because C phase is lagging behind phase A by 2 pi by 3 here. So, this is A C and then B. So, the phase sequence of the fifth harmonic is A C B. What about the seventh harmonic? Similarly, we can write down the voltage of the seventh harmonic V n 7, that is the seventh harmonic voltage sin 7 omega t. V B 7 is V 7 sin of 7 omega t minus 2 pi by 3, which is equal to V 7 sin 7 omega t minus 14 pi by 3. So, we can simplify this. So, this if we simplify, that is V 7 into sin 7 omega t minus 2 pi by 3. Similarly, we can write down the voltage of phase C. V C 7 is V 7 minus sin of 7 omega t plus 2 pi by 3. Now, if we simplify this, this will be V 7 sin of 7 omega t plus 2 pi by 3, because we have to bring the phase angle between 0 to 360, 360 is 2 pi. So, if we see the various voltages of the seventh harmonic component phase A, phase B, phase C, we see that here the phase sequence is A and then lagging A is B. B is lagging phase A by 2 pi by 3 or 120. Similarly, C is leading phase A by 2 pi by 3 or 120, or in other words we can say that phase C is lagging phase A by 4 pi by 3 or 240 degree. So, in this case the phase sequence is again positive, and we can say that the phase sequence is same as the fundamental, that is A followed by B followed by C. Now, we have a general formula. If M is the order of harmonic, for all positive component, positive sequence component, we can say that M is equal to 6 k plus 1. What is k? K is varying from 0, 1, 2 and so on. And for the negative sequence component, M has to be equal to 6 k minus 1. What is k? K is, we cannot have here equal to 0. So, we can start with k equal to 1, 2, 3 and so on. Here 0 mean this is the fundamental one. So, let us say if it is harmonics, we can say this is 1, 2 and so on. So, this is the order. If we have M equal to 6 k minus 1, we get the negative sequence components or the harmonics which produce the negative sequence field. If we have the order of the harmonic is 6 k plus 1, we get the positive sequence voltages. So, this is the order of harmonics, order of harmonics. Same thing here, we have order of harmonics. Now, if we just go back here, what about the triplen harmonic? The triplen harmonics are given by M equal to 3 k, where k is 1, 2, 3 and so on. And for triplen harmonic are all cophasal, they represent 0 sequence voltages. Now, we have seen that some harmonics are producing a 0 sequence component, some harmonics are producing the positive sequence component, some harmonics are producing negative sequence component. Out of these 3 sequence component, positive, negative and 0, the 0 sequence component does not produce a rotating field. Hence, the 0 sequence component does not take part in torque production. So, 0 sequence component does not take part in torque production. Or all these harmonics which are of 0 sequence, they do not take part in torque production. Now, let us try to see what happens here when the rotor is rotating at a speed of omega m, and we have, let us say we have a stator field. The stator field is rotating at its own speed. So, the stator field rotates from A to B to C. Let us say this is our stator field, and this is what we call to be the synchronous speed omega ms. The rotor speed rotates like this. This follows the stator field. So, we define a slip here. Slip is defined as omega ms minus omega m by omega ms. Now, this is the definition of the slip when we have only one frequency present here, positive sequence component. Now, when we have positive sequence component and negative sequence component, we have different slips for different sequence components, even for different harmonics. Now, let us see that what happens to the field when we apply fifth harmonic. When we apply the fifth harmonic component, what happens here? Now, fifth harmonic component produces a negative sequence component, a negative sequence voltages, which means the speed of the rotating magnetic field, if we say that this is our stator, phase A, phase B and phase C, this is A, B and C, and we apply a fifth harmonic component of voltage. So, we get a rotation from A to C to B. So, the rotation of the field in this case is in the clockwise direction from A to C to B, and this is the negative rotation. So, this is minus 5 omega ms. This is actually the speed of the rotating field, and the rotor is rotating as per the normal convention. We have the rotor is earlier rotating, and this is rotating at a speed of omega m. So, what is slip here? We define the slip with respect to the fifth harmonic as omega ms, but we have fifth harmonic. So, we multiply by 5, it is a negative sequence component. So, the rotation is in the negative direction, minus omega m. By definition, this is actually our synchronous speed, minus the rotor speed by the synchronous speed and the negative. So, we have this negative here. Now, that is equal to 5 omega ms plus omega m divided by 5 omega ms. So, this is the slip in this case of the fifth harmonic component. Now, we can replace this omega m from the previous thing here. So, this omega m can be written here if we do a simple mathematical readjustment. We will see here this is equal to 1 minus omega m by omega ms. So, if we want to find out what is omega m is equal to, we can take it to the left hand side. So, we have 1 minus s into omega ms. So, we can replace this omega m, the speed of the rotor, by this expression 1 minus s into omega ms. Omega ms is the synchronous speed and omega m is the rotor speed. So, this is the rotor speed and this is the synchronous speed. Now, what we do here, we substitute the value of omega m from this in this equation, that is equal to 5 omega ms plus 1 minus s into omega ms divided by 5 omega ms. So, we have some cancellation here, omega ms will get cancelled. So, what we get here is 6 minus s divided by 5. Now, this is the slip for the fifth harmonic. Now, we can find out the value of s from the normal rotation. What is the normal value of s? Now, for the fifth harmonic component, the slip for the fifth harmonic component is given by 6 minus s by 5. Now, this is something which is close to 1. We will see that this is close to 1. This should be something higher than 1, but not very far away from 1. So, it is something like 1.1 something. Now, let us find out the same thing for the seventh harmonic component. Now, if we find out the seventh harmonic component slip, the seventh harmonic component is a positive sequence component. This is a positive sequence component. So, this will produce the positive sequence voltages. So, we can apply these voltages to the stator of the induction motor. We have phase A, phase B, phase C and the neutral here, and we have the rotor. The rotor has got the short circuited bars for squirrel cage structure. So, the seventh harmonic rotates from A to B to C. So, this is the rotation of the seventh harmonic field. The stator field will rotate at a frequency which is 7 into omega ms, and the rotor usually rotates in the same direction because of the positive sequence component, the fundamental component. Now, here we find out what is the slip. So, what is the slip for the seventh harmonic voltage or the seventh harmonic component here? That is equal to the speed of the synchronous speed is 7 into omega ms. It is a positive speed. So, we have plus 7 omega ms minus the rotor speed. So, this is our synchronous speed divided by the synchronous speed, which is 7 omega ms. Now, we represent this and we replace this omega m by 1 minus s into omega ms divided by 7 omega ms. Now, if we simplify this, what we get here is 7 minus 1 plus s by 7, which is equal to 6 plus s by 7, which is also a quantity which is less than 1, because slip is usually from 0 to 1. So, this is also very close, not very far away from 1. So, this is close to 1. So, what we see here, that the slip for the higher order harmonics are close to 1. So, this is the slip for the seventh harmonic component and this is the slip of the fifth harmonic component. So, we can arrive at a very general formula if we want to find out for any harmonic m. So, we can say that for mth order, we can say that this is m into omega ms plus minus omega m by m into omega ms. So, this plus sign is for the negative sequence component and the minus sign is for the positive sequence component. So, for harmonic of higher order the sleep is close to 1, but we have to calculate for a given frequency. Now, let us see what is the effect of this on the operation of induction motor. Now, to analyze the effect on the induction motor operation, we have to take the help of the equivalent circuit. The equivalent circuit for mth order harmonic, equivalent circuit for mth order harmonic. So, we do not have the, we are not discussing once again the fundamental component, we are only discussing about the mth order harmonic. Now, the frequency here is m times into f. So, this is the frequency because we have the mth order harmonic. So, we draw the equivalent circuit, the stator resistance, the stator leakage reactance and the rotor leakage reactance and the rotor resistance. So, this is the equivalent circuit. Now, this is the stator resistance for the mth order harmonic and the reactance is Xs, but for the mth order harmonic the frequency is m times f. So, the reactance here will be m times into Xs. In the rotor also we have XR prime, but here we have m XR prime. What about the rotor here? The rotor resistance is R for the mth order harmonic referred from the stator side divided by Sm. Sm is the slip of the mth order harmonic. Similarly, we have the magnetizing reactance here, which is m into Xm, and we put a J here because this is the reactance, and the input is per phase voltage, the voltage is Vm. Now, we see here that the input current here is ISM and the rotor current here is IRM. Now, if we see in this case m is a large quantity. So, when m is a large quantity, we can say that this circuit is predominantly a reactive circuit and the magnetizing reactance is also quite large. So, we can represent this only by reactance, and Sm is something that we have already discussed, that Sm is close to 1. So, this is this slip is high here and the rotor resistance is a small quantity. So, the resistance of the circuit can be neglected with respect to the reactance. Furthermore, since we have a reactive circuit, the power factor is poor. So, the power factor is poor, power factor is poor and the torque production is negligible. So, the average torque production is very small due to poor power factor. So, the harmonics they do not contribute to any average torque significantly. So, we can reduce this equivalent circuit to a reactive circuit where we have primarily the reactance of the stator and the reactance of the rotor, and we can ignore the magnetizing reactance because this is quite large here. So, this is Vm. So, what we can say here, this is ISM, this is m into Xs and m into Xr prime. So, the value of ISM can be given as Vm by m into Xs plus Xr prime. I am talking about the magnitude. So, there will be some current here, So, what is the effect of the harmonics? The effect of the harmonics is to increase the losses of the system. The losses are increased. In addition to that, there will be torque pulsation, because we have various the rotating field. This rotating field will interact with each other to produce pulsating torque. So, the effect of this is increased losses in the motor and pulsating torque. So, these are the effect of harmonics on the operation of induction motor. There is very little average torque contribution from the harmonic components. The harmonic components are mainly responsible for heating of the motor by increasing the losses, both core loss and the copper loss. So, the motor has to be derated when the input supply is not sinusoidal. So, we stop here for today's lecture. We will continue our discussion in the next lecture.